class of the 9 o'clock hour. All right, so we started talking last week about stress, normal stress and shear stress. I hope I put that there. Sorry, just making sure I left myself the blank. Oh boy, this is gonna be fun. Sorry, I need to cheat and make sure that I have a blank space at the end. And okay, thank you. All right, so we started last week talking about normal and shear stress. Those who should be reviews from statics, or so I hope. Can you tell me can anyone give me a quick recap of what normal stress is, or at least what makes it up, or how you'd compute it, how you describe it? Yeah.
It's stress that's acts perpendicular to a force.
Stress that acts perpendicular to a force. Result. Okay. Say it again.
Stress that results from a force that's perpendicular to it.
Stress that results from a force that's perpendicular to the stress, or it's perpendicular to a face. Yeah. Okay. So normal stress. I have my block. I have a force pressing down on it. If I take my section in the middle of the block, I have some distribution of force in that perpendicular to that face. Force over that area gives me my normal stress. Cool. And shear stress would then be what? Yes. Okay, so instead of the force being perpendicular to the face, the force is now parallel to the face. Yeah, is that what you're saying?
Yeah.
Okay, cool. Yeah, that's shear stress. At least that's a that's the kind of like average shear stress that we have now. Cool. Now, when you who apply stress to something, the object doesn't stay rigid. That's another lie from statics. Like nothing is static. We just approximate it like that. So the question that we're going to answer today is what happens? How do they deform? Or if you want to throw some terminology at it, how do they strain? And then we're going to look at we should get there. At how stress and strain are related via Hooke's law, which should be a familiar term from physics, or statics really, because you applied it to springs in the past, right? Like an F equals kx kind of thing, where you have force is proportional to displacement by some spring constant like thing. Well, materials are really just a whole bunch of little springs working together, so we can approximate how materials deform in response to a stress with the same sort of a relationship. And hopefully, if I erase everything, my computer won't crash. Okay, so we did that. Great. So let's start. Yeah. Okay, so I already said some of this. Again, this is all driving towards kind of the overarching goal of trying to figure out when things break, how do they break, and how can we design things so that they stop short of the point of stop short of the point of failure. Another question that we're going to ask this week, if this is a plot of how much load is being applied to a body versus how much deflection or how much deformation there is, we're going to start asking questions about some of the more interesting points here. So like obviously like these are probably kind of important, right? Like where there aren't any more data, that means that the thing probably doesn't exist anymore. So it's probably an important part. But what about this? What about this spot here? I mean, the load versus deflection curve's pretty linear until that point. So something must happen there that is interesting. So these are all things that we're going to look at, hopefully today, if not on Thursday. Okay. All right. So deformation. This is related to strain that I mentioned before. Deformation, and at least in a linear case, is defined as the amount of length contraction or extension due to a load. However, if I have like a meter of material and it extends a foot, that'd be different than if I had like an inch of material and it extended a foot, right? Like if I had, it's called, like if he had a piece of you know those Armstrong Willie things, like little rubber guys, you yank their arms and they go out for like 100 feet. You guys ever play with those? Am I just that old? What you call it? Like there's the little rubber figure guys, and you would pull on their arms and it extend for like 50 feet. Am I that old? Dang it. Okay. Anyhow, the point I'm trying to make is that deformation by itself doesn't. I mean, like, it's nice to know how far something's stretched or how much length it's changed by, but that doesn't really give us an idea of what's actually going on. Kind of in the same way that, like, if I have a piece of material like this, and I apply a certain force to it, it'll bend a fair amount, right? But if I apply the same stress to something like this, it doesn't really bend nearly as far. And one could ask, well, one does ask, why? Why do you think that the same force on this little guy causes it to break, pretty much, and the same force applied to a textbook doesn't really do a darn thing? What's the difference between these two, just on a bare physical scale? Thickness. Okay, so how big the thing is. And based on what we know about stress, if you have something that's larger, do you have a greater or lesser stress? Less, right. So stress is actually, so we formulate stress on a similar idea to how we formulate strain. Instead of saying we have some load, and if I have the same load applied to, I can apply the same load to a book, I can apply a load to a tiny I-beam, and get two different results because they're different in sizes. Because they're different sizes, we can kind of capture that in stress. So you might say that we're normalizing force by cross-sectional area to create stress. And that shows us the difference between these two items when I apply the same force. Does that make sense to everyone? Okay. In the same way, strain kind of says, well, I can have two different objects that have deformed by the same amount, but what's actually happened to each one's fundamentally different. Like my little 1 inch thing that's deformed a foot, it's changed a lot more than the 1 meter thing that's changed by a foot, right? One has been extended by 12 times its own size. The other's only been extended by 1/3 its own size. So we capture that in strain, which we write as epsilon. And epsilon or strain is computed by normalizing deformation by the length of whatever the object, the original length of whatever the object is. This is at least for normal strain. Okay. So this is strain in response to a normal stress. You have a normal stress, you have a normal strain. Okay. So the all-important question of units. And they're pretty weird because deformation is in units of length, right? And length is in, well, units of length. So you might say that this is unitless, and it is, but we have to call it something. So you have a plethora of different ways of talking about it. You'll see these sometimes referred to as strains, or because materials don't deform that much, generally speaking. There's generally not a lot of strain. You often see you often see it referred to in terms of micro strains. So whatever this result is times 10 to the negative 6. You might see it referred to in lengths per length, and they're inches per inches, stuff like that. So let's say that I have a beam here, and it deforms, and this is, all right, let me write some lengths here. And this is a foot long, and it deforms by 1 inch. Okay. Let's, for sake of argument here, we're just going to have this be in the same units to begin with, so we don't have to convert it. What would the what would be the strain in this beam if it's deformed 1 inch and 1/12, like it's 0.083? So I think it's 0.083 or something like that. So it's 0.083 strains, you might say, which is a whole lot of deformation, like micro strains. Or because I could also say that this is what 83000 I could also say that this is 83,000 microstrains. You see how I got there? Or that'd be another, that'd just be another way of saying that. The units are kind of weird, so just wanted to go over them quick. All right, so that's strain in a nutshell. But that's not really exciting unless we can apply, unless we can relate it to stress, right? And that's where Hooke's law comes in. Now you probably remember this, but the relationship is pretty much the same thing, but stress and strain are being related not by a spring constant per se, but something called the modulus of elasticity. Now, just kind of looking at this, units of stress are in, or what's called our force per area, right? Units of strain are length per length. What must the units of the modulus of elasticity be? Say again?
Units of stress.
Why?
Because the other one's useless.
Yeah, you got it. We have to end up, so if I rewrite that equation in terms of units, and I do it in, say, English for some crazy reason, I have like pounds per foot squared on one side equals X, let's say, times like inches per inch. Well, that cancels out to nothing. The units must be in the same units as the stress. Awesome. So that's PSI, gigapascals, megapascals, whatever your favorite unit of stress is. You also, typically, you'll see moduli of elasticity, also known as the Young's modulus. For some reason, there's about 2 or 3 names for every single constant in this field. Don't ask me why. Typically, you'll see this value on the order of millions of pounds per square inch, so MSI, or I might say on the order of gigapascals. So these are usually really, really large numbers. All right. Cool. So let's try putting this into practice. If you go back to your notes from last week, you should have all of the numbers for this laying around. If you need a reference, I think we already found what 127.329 kips is the is the internal reaction of the hydraulic piston. If we assume that everything's the same material, and remember, and actually I didn't say that before, and assume that the diameter of, actually we don't care about that one yet. We assume that the diameter of this ram is 10.5 inches, and that this ram is half the length of the arm, and the arm is 36 feet long. So that means that the ram is 18 by corollary. The question is, what is the strain and what is the deformation in that ram? And we don't have to go through too much more, right? Because we know that this ram is this ram is pinned. So everything here is a pin joint. It's pinned top and bottom, so it's a two-force member. So if we know the reaction at the top, we know the reaction at the bottom too, right? We all on board with that? Cool. So we want to find the strain and deformation in that ram. So how would we go about it? What would be kind of like the first step?
Well, we know what the stress is, right?
We know what the reaction force is. We have to find the stress, isn't it? Right. What kind of stress must it be? Right, because it's a two-force member, therefore the force must be oriented down the axis of the object, so everything's a normal stress. Isn't that awesome? So, how do we find normal stress? Cool. So, what is it? We have more than one person do it. Just make sure that our answers are all copacetic. That'd be awesome.
Yep.
1470.5 psi. All right. You sure psi? Just making sure.
Yep.
Okay. Yeah. Why?
My chips to regular pounds.
Okay, so you did 127,329 kips divided by whatever the area was. Cool. Yeah, yeah. Okay, so did you get a similar answer?
Oh, I'm still.
Oh, you're still doing it. Okay, cool. It's 127.329 kips, because yeah, it's 127,329 pounds. Cool. Okay. Well, for now, assuming that's correct, what's our, it's called how we find strain given this. Remember Hooke's law? What's Hooke's law for materials? Cool. So if we have sigma equals E epsilon, or stress equals Young's modulus times strain, what do we got? What do we need? And how do we get there? Yeah. Yep. Yep. Yep, so as soon as you get Young's modulus into units that match with your stress, you just divide the two and you get something tiny, right? How tiny?
5.07 times 10 negative 10.
Okay, cool. I can believe that. Say it one more time.
5.07 times 10 negative 10.
Okay. Units?
Units of inches per inches.
Cool. Or strains, which is, I mean, it's important to put because some people use microstrains and stuff as their base unit. So it's important to always put your units, even if, ironically, there aren't any units. So cool. So that's our strain. Do we check out with the stress number?
Yeah.
Cool. So we got our strain. How do you find deformation? Multiply by the total length. Absolutely. He doesn't matter what the units of the total length are. Correct, because there aren't any units to cancel out. So whatever you multiply it by are going to be the units of your answer. So in this, in this case, it's like, oh, what? 10 to the fourth, 10 to the third, like about a foot. 1 times 10 to the negative third feet of deformation, or something like that.
Almost. It's 9 10,000.
Okay, 9 10,000s. Great. 0.009 feet. Cool. So that's how far that RAM is actually shrunk by, which in the grand scheme of things, it's not that much, right? And this is why normally, like in statics and everything, we say, hey, everything's rigid because the deformations are freaking tiny. At least for stuff like steel and rock and all that kind of jazz. When you start getting into the more ductile stuff, it gets more interesting. So that's a pretty straightforward application. But what if we step back for a second, make sure I get all the stuff. So what about the other two bits of this? Here it gets a little bit more interesting. We're going to ignore shear stress right now, just for sake of practice. We just look at normal strain and normal stress. But again, that doesn't really show up that well. That shows up marginally better. So we know our reaction force. It's that 127.329 kips thing. We have somewhere written down on the force here because it's really just that. But we have this weird transition spot, right? Like if I take sections along here and start to find what forces are acting on each section, that's going to change going down the arm, right? So let's see how that change. how that changes. If I took a section here, so right here, so and I say I'm going to go until this pin here, okay? Because know the forces at each end here. So I know the force at the pin joint. I know the force at the counterweight. Well, this is, I want to say it. Yes. Okay. Wait. Can I say that? Oh, I can't say that. Never mind. In order for, if I have that section broken in here, I know that force on one end is coming entirely as a component of the force created by the counterweight. What's the force that's acting on the other end of that section? Or what forces are acting on the other end of that section? What forces do I have to put together in order to figure out what's going on here? Or would I? Okay, so you have the force of the ram here. And it's acting at 20 degree angle. Is that all? Normal force of the other member? Where's the other member? Which?
Like I was thinking about like the base of it.
Okay, so like the reaction force from that support? Yep, so that guy is in there too. So that's not actually directed just in that just that way. It's some combination. But in order for this element to be in static equilibrium, what must be the sum total of all the forces on this side? Right. All the stuff over here has to equal whatever's on this side. In order for that element to be in static equilibrium. And we could do out the math. We could do all of the statics here and figure out what the reaction of that joint is, which would be a good thing to do. But for up here, we know because we know that these two sides must be the same in order for this element to be in static equilibrium. We can just find what the right side of the equation is. We can find out what contribution this counterweight has on the normal force acting on the top bit of this arm. All good with that? Cool. Nods give assent. I like it. Shrugs give assent too. So what is the component of this counterweight that's acting as a normal force on this arm? How would we find that?
The angle between the arm and vertical is the same as the angle between counterweight and vertical.
Right, geometry is awesome. Therefore, if I have a vertical line here and a vertical line here, this angle and this angle are the same. So this is 32 degrees. And what do I do now?
Repeat it both sides, 32 times its force.
It would be. So what is it?
16,560.
I'm sorry. One more time, please. 16. Okay. 961 lbs, pounds force. Cool. All right. So get rid of a bunch of the distracting crap here. All right. Cool. So that means that if I redraw this a little bit, 5 element here. Come on. Really? That's annoying. Okay. So the force poke, some of the normal force poking down from the top is equal to force of the, which called the weight of the counterweight times cosine of 32, which is this, which is this number, and that's the only force that's acting on the top, assuming that we're ignoring the distributed weight of the arm for right now, which we are. And and because it's the only force that's acting on the top in our idealized little world, well, that means since that the force pushing up from the bottom must be the same thing in order for Newton's third law to be happy and this arm not to be doing weird noodly things and moving, and therefore this is the normal force. So how do we find normal stress? Assuming that the arm itself is 29.25 inches in diameter. It's like stress to the upper arm. We have our force. We have our diameter, which we have a constant diameter section. And that means what? Yes? 25.24 psi. We have agreement on this. We think it's weird. What do we think? Cool. That's really, really stinking low, right? Which is kind of cool because it's 20,000 pounds, and I mean the arm just doesn't seem to care. I mean, it's 25 psi. I mean, like atmospheric pressure is almost that. Like that's how much pressure is pressing down almost pressing down on your skin right now. It's kind of cool, almost twice it, but whatever. Like that's not that much in the grand scheme of things. In part because of this area being so much larger. I mean, it's almost 3 times as large as the area of the ram, and the force is a lot lower too. So, and sorry, the diameter is 3 times more, which means that the area is about 9 times more, because it goes up by the square. So cool. So we have not a lot of pressure there, but that's the top half. What if I took a section now through like the bottom half of this ram, so like around here, how would I find the forces acting on that? You got internal reaction here. You have that force there. That force there. Force there. I want to be consistent. How do I find forces acting on the element on the lower part of the arm? Which are you saying? Wouldn't it be the same force? Okay. Okay. So what? So walk me through it. Force the ram's not there anymore. Correct. So I have, this is like my ram. What other forces are yanking on this guy? And give me a direction for everything. Like this one's going that way. Okay. So if I was, I'm just going to draw a line and start drawing forces that his pulling on it, but they're all acting on the element. Okay. That's like a 32 degrees. What else? Okay, so then we have some reaction force here. Okay, cool. So, how might we go about figuring out what's actually going on here? What do we know? What don't we know? What do we need to find? And how can we get there? Okay, so let's start. Say again. Okay, set some things equal to each other. Like what? What do we know have to be balanced? Right. Everything, in order for this element to be in static equilibrium, everything here must equal everything here. At least in terms of the normal force, at least in terms of the normal forces. It has to do in everything else, but there's more involved. So in terms of normal forces, everything on the left must equal everything on the right. So that means that I can find this by determining, I can find everything on the left by determining everything on the right, correct? And that gives me all the normal forces acting on the thing, that gives me all my stresses, that gives me my strains, blah, 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 blah. And conveniently, I know everything on the right, correct? I know the force due to the ram, I know the force of the counterweight. So how do we get there from here? I already have the force of the counterweight that's acting parallel to the arm. That's the 16.961 kip thing that I found before, or that someone found before. So let's start writing stuff in. So if I have FCW parallel, so I don't have to write that a billion times, 16.961 kip. I also have force of the ram parallel to the arm. It's equal to force of the ram, what, cosine 20 degrees, same deal as before. Now, do I add or subtract these numbers, or do I multiply them? Like, what do I do with these? Subtract them. What from what?
Well, because it's on the right side, I'd say you subtract the counterweight down with
Okay, so are you saying that? Other way around. Okay, so that. Cool. Okay. To be honest, half of it's just call it half of sign conventions are arbitrary. The important thing is just the word consistent. So in the last slide, we computed the stress for forces that were acting kind of like that, right? We looked at a section at the top of the arm. The counterweight's pulling down. It's putting the top of the arm in compression, right? So it's pushing down on the arm. It's not trying to stretch it. It's trying to crush it. That's compression. And we used a positive sign for that. So if we used a positive sign for compression, let's try to keep the same sign, this same kind of convention here. So in this case, our compressive force is our counterweight, and our tensile force, or the one that's pulling the arm apart, is the ram. So let's make that our sign convention, just to be consistent with before. Typically, you'll see a compression stress is negative, but just to be internally consistent for now, let's make big compressive stress as positive. That does not show up at all. I need to write that in white. I'm sorry. All right. So compressive stress is positive for right now. I get that. I divide by my area, and that should give me a stress, a normal stress. Anyhow. So what do I get? I hope it didn't crash. Yeah.
Negative.
Okay. And what does a negative number mean?
Getting stretch.
Yes, it's intention. Yes. I'm sorry, he crashed for a second. And the number is what? What do we get?
We got the same number versus outside.
Okay, so it means that someone used less sig figs. It's all decimals. Okay, all right.
Yeah, 152.8.
8 psi, and say again?
She got 0.15.
Yeah. So let's say what's the what's the factor of the difference here? Right, which is the same as a KSI, so it's probably just difference in units. So 152.8 psi or 0.1528 KSI. Cool. If I was to find a strain from, and this is negative in this case, there it goes. It finally crashed. Tried to move between too many slides. So the strain generated by this is what? If the stress in the lower part of the arm is negative 152.8 psi, strain in the lower part of the arm is what? Millions of pounds per square inch. Yeah. Yes.
5.26 times 10 to the negative 6.
5.26 times 10 to the negative 6. That sounds. Yeah. Sounds. Yeah, it sounds about. Yeah, it sounds about right. And then if the arm's 36 feet long, this should be the straightforward part. What's the deformation in the lower part of the arm? Yep.
1.8 times 10 to the negative 4 feet.
And how did you get that number? Well, it's only yeah, because it's not the force. So this strain only corresponds to the region where our where our force balance was valid, and our force balance is only valid for this part of the arm. So only that part of the arm is going to strain by that amount. Strain is a unitless number, but you have to say what its order of what its order of magnitude is. So if it's strains, micro strains, thousands of strains, etc. It can be negative, actually. And here, you're right. This should be negative. This should be negative, because our stress was negative. So it's stretching. It's not compressing. You're right. Okay. So so we have this strain. It's like on the bottom part of the arm, which is 18.7 feet long. So if we multiply those two together, we should get our deformation. Any questions on that? Okay, cool. That's all I got. That's all I got for today. Thanks for stopping by.